to a large degree, a physics course like this one's involved with motion of things. We spent a lot of time looking at variables like position and velocity and acceleration and how things might move around and crash and conserve energy and that sort of thing. Well, there's another branch of mechanics that's known as statics. And what statics is concerned with primarily is how do you make things stay still? It's actually, believe it or not, a whole branch of physics and engineering. Now, you might ask, well, why would we want something to stay still? Aren't we always interested in motion, like cars and balls and airplanes and that sort of thing? Yes, we are, but we're also interested in things staying still. Like, for instance, it's a good idea if you have a house, that the house is built in such a way that it stays still. Or if you have something like a bridge like this, say, spanning a big canyon like this, there's a bridge here, maybe it looks like this. It's a really good idea if this bridge is going to be safe and so on, that it stays still. It could be some sort of suspension bridge or something like that. The Golden Gate Bridge in San Francisco is an example. These are examples of engineering feats, certainly made with ideas from physics and engineering, but it's a good idea if they stay still. We don't want these things to move. And that's what the idea of statics are about, is how can you analyze and look at objects that are not moving and understand something about their internal structure. So, if we don't want something to move, here's some of the ideas about how we might accomplish that. If we don't want the house to move or we don't want the bridge to move, here's how we might accomplish it not moving. What we'd like to say is we're going to say, all right, look, I'm going to say that its initial x and y velocities are 0, and z if you happen to be working in 3 dimensions, but we'll just stick in 2 dimensions because it's general enough. So if you can possibly set or build a thing so that it's already not moving, you just don't give it any velocity. Now, I don't think that's very hard to do. You can just put 2x4s and so on at your job site so that they're not moving. I think that's okay to handle. But the trick then is once you have it not moving with no velocity, you also want it to not have any acceleration. You want ax to be 0 and you want ay to be equal to 0. Now, this side over here, can be the tricky part right here. Because like I said, it's easy enough to bring a bunch of I-beams or 2x4s to a job site and not put them down at 50 miles per hour, just put them down at rest. You can easily achieve this. But can you achieve this here forever? Can you arrange the 2x4s and the I-beams and the bolts and the concrete and that sort of thing, or whatever you envision goes into building a house or a bridge, such that the accelerations remain 0 forever? Why is that important? Because we know that if things are going to move, like fall or roll or something like that, then it'll have something like v will be vx plus a times delta t, ax times delta t, and vy here will be vy plus ay times delta t. Good old equation 2 from much earlier in this course here. So in particular, all we're saying here is that, look, if you have a 0 initial velocity here, this vx and vy are the initial ones, 0 right here, if you want them to stay 0 for all time, in other words, you never want these parameters, the velocities later in time, to ever acquire any values, then you have to ensure that the ax and the ay are 0, because time is going to keep marching on here. This is your clock right here. These times here can be something like 1 day or 1 year or half a year or 10 years or something like that. If you really want the house or the bridge just to sit there forever and not move, you have to ensure that no matter what time interval you put in here, in the future you can always ensure that these v's over here are going to be equal to 0. That's what statics is all about. And again, the trick here is ensuring these accelerations are 0. So the way we can accomplish that, or to get some sort of understanding down, or analytical technique down on this thing, is to just fall back on Newton's laws. He says, hey, look, the x accelerations are the sum of the x forces divided by m, and the y accelerations are the sum of the y forces divided by m. These are Newton's laws right here. So we're going to have a special form of those in this case here, because we want these accelerations here to be 0. We want this to be 0, and we want this to be 0 to ensure that our objects will never obtain any velocity and start moving. And if we rearrange these a bit, then we can see that what we end up with then is the sum of the x forces are equal to 0 and the sum of the y forces are equal to 0. So these are our sort of statics forms of Newton's laws, and these will be the driving equations, for the most part, for solving statics problems. You want to look at a system and identify all the x forces, add them up, set them equal to 0. Then you want to look at and identify all the y forces, add all those up and set them equal to 0. And if you do that here, this will result in no translation. And I'll say no translation if, of course, you can assure us that your v sub x was 0 and your v sub y is equal to 0. Because certainly you can set your 2x4s and the I-beams down moving at 50 miles per hour, then if you sum all the forces on them, they're equal to 0. The only thing you can guarantee is that it'll maintain the 50 miles per hour. So no translation if we also ensure that these velocities are 0, which is easy to do. Again, we can just set things down nice and easily at rest on the construction site. So this will guarantee no translation. Of course, if you're not up on your physics lingo here, the word translation here actually means just to move. Okay? So no movement or no translation if you can assure that's true. So there's two status equations that we'll use, but that's not the end of the story because there's another way that buildings and bridges and so on can move that we don't want them to. So I'll go ahead and erase this for now. And there's one more little bit we have to look at here in order to really be ready to start looking at statics and ensuring that things are going to be safe for people to go in and bridges are going to be safe for cars to drive over and so on. There's another condition here. Certainly we don't want the house to move, and that's we've sort of established that. So we don't want the house, like when we come home from work, we really don't want our house, say, to be over here or up in the air or anything like that. We'd sort of like to avoid that. Okay, so that's sort of what we are guaranteeing by setting the house at rest and ensuring that the sum of the forces on the x and y direction equals 0. We don't want that to happen. But there's sort of another unpleasant mode that we could possibly have for our house, and that's particular if the house was sitting here and the house started to tilt over like this. So say I came home from work and my house looked like this. This would be bad too. Or in the case of the bridge right here, here's that canyon, and suppose the bridge suddenly fell or something and looked like this later in the afternoon as the rush hour commute started. That would be bad too. So what this case is here, in this case here, is that the objects haven't moved appreciably, or maybe even at all. They haven't moved. They're still about in the same position. Like here's this nice big tree right next to my house right there. I guess I could put a little green in there to make it look a little nicer. Here's this tree here. So the house hasn't moved very much relative to the tree. There hasn't been any translation. So maybe I am ensuring that the x and y accelerations are 0. But what has the house done? Well, it is rotated. We want to make sure that doesn't happen either. So that's the third aspect about statics, is you want to make sure that the object can't rotate either. And the way you ensure that is an equation very much like the sums of the forces, but what you want to ensure now is that the sum of the torques are equal to 0. Torque is technically a vector in there. Now, where does this equation come from? Well, what it's really saying is you want the angular accelerations on all the objects to be 0 as well. And this is just like in the other example where we said we want the accelerations to be equal to 0. Because if you can ensure that the angular accelerations are 0, then the object will never be able to rotate, because we know that omega is equal to omega naught plus alpha times delta t. So if you can ensure that this alpha is 0 here, and we start putting in delta t's like 1 day, 1 year, 1 week, 10 years, whatever, as this sort of ticks on, which we have no control over, if omega naught is 0, in other words, we build a structure here, a house or a bridge that is not already rotating, then if you can ensure that alpha is equal to 0, if you can ensure that this is true, then this will be equal to 0 forever. And that's sort of what we like to ensure here. So we're just ensuring that alpha is equal to 0, and also we're just going to remember this simple relation, sort of the Newton's law version of this, that alpha is the sum of the torques divided by the moment of inertia of the object. That's what alpha is equal to. And so if we want alpha equal to 0, we can solve for the sum of the torques. And indeed, we are sort of left with this idea right here, that if alpha is equal to 0 right here, then we are left sort of with this condition right here, which is the last one we need to solve statics problems. So there you go. There's your setup for solving statics problems for you. Those are the 3 guiding equations you'll need to solve statics problems. I'll just end this video by summarizing these things here. Statics is all about objects staying still. If they're staying still, we like no velocity in the x-axis, no velocity along the y-axis, and I guess we want omega to be 0 also. I'm not sure exactly how you're casting your problems, but in this case here we'd say omega z would be equal to 0, because if we focus on objects in the xy plane, typically we're avoiding z-axis rotations, but of course omega can be about any axis. We're also leaving out v sub x here, but in general we want the full vector velocity to be 0 and the full vector rotational speed to be 0 as well. And if that happens, we can ensure that by ensuring that the sum of the forces in the x direction are equal to 0, the sum of the forces in the y direction are equal to 0, the sum of the forces in the z direction are equal to 0, ensure all those are 0. We'd also like to ensure that the sum of the torques around the x-axis are equal to 0, the sum of the torques around the y-axis are equal to 0, and the sum of the torques around the z-axis are equal to 0. These are our equations for equilibrium. It's 6 of them. Boy, it looks like a headache, but in most physics problems, say at the elementary freshman level, you're really going to be concerned with just 3 of them. This one right here, no force along the x-axis. This one right here, no forces along the y-axis. And this one right here, no torques along the z-axis. And the reason being is because most problems in freshman physics are worked in the xy plane like this. This is always the x-axis, this is always the y-axis. So if you had your house it would very likely be sitting here like this in the XY plane. Here's how we'll ensure it won't move using those two equations right here. And then, of course, the z-axis sticks out like this. And we want to ensure we don't get any rotation either this way or this way about the z-axis. And by setting the torque equal to 0, that's how we'll ensure that. So there you go. They're statics. Things are going to stay still. We don't want them to move. And in a physics class like this, we can ensure that as long as these two equations are satisfied and that one's satisfied as well.